This video is going to take you through chapter 3, sections 4 and 5, which is going to cover things like perpendicular lines and then graphs of lines and slope. So we start with 3-4, which is called proofs with perpendicular lines. Obviously, a good indication that we're going to be trying to prove things about perpendicular lines. So first of all, definitions here. This one says the distance from a point to a line. And the distance from a point to a line is the length of the perpendicular segment from the point to the line. It's the shortest distance between the point and the line. So if you had just seen, let's say, for example, point A drawn here, and then you had the line K, and it asks you to find the distance from point A to K, you can't just measure anywhere. Like I can't take a ruler and measure any of these segments. The shortest or true distance from the point to the line is the perpendicular segment that it connects that point to the line. So you'd have to have a right angle there. This first example says find the distance from point A to line BD. So A is here, line BD is this full line here. So the first thing is there's 3 segments drawn here. The one we actually want to find the length of is the perpendicular segment. So we want to find the length of AC because that would be the distance. To find the distance, we use the distance formula, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. If it was a vertical or horizontal line, we would just count the units, but because this is slanted, you can't do that. So I'm going to use these 2 coordinate points. It doesn't matter which ones you make, the 1s or the 2s, so this could be your x1, y1, x2, y2, or reverse, as long as the numbers stay together. And then I plug them in. So square root of x2 is 1, minus a negative 3, because that's x1 squared, plus x, or y2, which is negative 1, minus y1, which is 3. And this minus a negative becomes plus. I end up the square root of 4 squared plus negative 4 squared, the square root of 16 plus 16, which is the square root of 32. Now, if it wants your answer to be rounded, you can type that into the calculator and you can approximate it. You can also approximate it by seeing which 2 perfect squares it's between. So it's in between square root 25 and square root 36. It's a little bit closer to the square root 36, so we would estimate it to be closer to the square root of 36, which is 6. And we would say this is maybe like a 5.6, 5.7, something like that to approximate. If you're going to keep it exact, you have to take that square root of 32 and you have to see if you can simplify it. So we use the factor tree. 2 goes into 32 16 times, and 2 goes into 16 8 times, and 2 goes into 8 4 times, and 2 goes into 4 2 times. And then for each pair of an identical number, we bring that number to the outside. So 2 2s means I'm going to bring 1 2 to the outside, another 2 2s, another 2 gets brought. This 2 that doesn't have a partner stays underneath. So I multiply out, and I get 4 square root 2. You could have also said from here, if it's 2 and 16 and you can square root that 16 as 4, you could have brought it out there. It doesn't always happen that there's a perfect square. So you can always use that. When you can't figure it out, you can use your factor tree. Okay, perpendicular bisector. So new vocab term here. The perpendicular part means it's 90 degrees. The bisector means that it cuts it in half. So a perpendicular bisector of a segment would be perpendicular to that segment. So in this case, if we're saying that N is the perpendicular bisector of PQ, then it's perpendicular to PQ. You see the right angle there. And it is also cutting it into 2 congruent parts, which is why these congruency marks are here. It hits line PQ, it hits line PQ at its midpoint. So we're saying the midpoint is M, and it's that those would be 2 congruent segments. PM would also equal MQ. So all of those things can be determined if something is the perpendicular bisector. So proving theorems about perpendicular lines, here's one theorem that we can use that says linear pair perpendicular theorem. If 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if I have 2 lines, like here, 2 two lines, and they intersect to form two congruent angles. This one is congruent to this one. If you think about it, those two lines would form 180, or the two angles would form 180 degrees. If they're congruent, I would cut the 180 in half. That's 90, and because it's 90, it means it's perpendicular. This just says it all in one. So linear pair perpendicular theorem. Proving theorems about perpendicular lines continued. This one's called the perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other line. So if I know that these two lines are parallel and J is perpendicular to H, then J would also be perpendicular to K. Long way around is that these angles, 1 and 2, would be corresponding. So if those two lines are parallel, those corresponding angles are congruent. If one is 90, the other one's 90. You could have done it that way. Or you can use this one, kind of a shortcut, perpendicular transversal theorem. That just says if it's perpendicular to one of two parallel lines, then it's perpendicular to the other one as well. Okay, this one's called lines perpendicular to a transversal theorem. It's kind of piggybacking on what we just said, except this time you know they're both perpendicular to the same line. So in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So in the last one we said if they're parallel, perpendicular to one, it'd be perpendicular to the other. Now the given information is that they are perpendicular, both perpendicular to line P, which means that they would be parallel. Again, based on previous knowledge, those are corresponding. If they're corresponding and they're congruent, then the lines are parallel. You could have used that way. Or you can use this one shortcut, lines perpendicular to a transversal theorem. All right, example 2 says this photo shows the layout of a neighborhood. Determine which lines, if any, must be parallel in the diagram and explain your reasoning. So hopefully you notice these right angle marks. If I look at just these two here, if this line is perpendicular to this line and this line is also perpendicular to that line, then P is parallel to Q. And same goes for this angle and this angle. If T is perpendicular to Q and S is perpendicular to Q, then S is also parallel to T. Now, I don't have any marks on that last line that U, so I can't use those. And the reasoning here is that last theorem, which says lines perpendicular to a transversal theorem. If you don't remember the name, you can always explain it. If if two lines are perpendicular to the same line, then those two lines are parallel. All right, 3.5 is the last section in the chapter, and it is using slopes of lines. Hopefully this seems relatively familiar because you talk about slopes a lot in Algebra 1. And if not, here's a good refresher. So we talk about the definition of slope first. Slope of non-vertical lines is the ratio of the change in y, or the vertical change, to the change in x, or the horizontal change. It's also known as rise over run. If you have two coordinate points, you can either count your rise and your run, or you can use this, y2 minus y1 over x2 minus x1. And the symbol for slope is m. Don't ask me why. There's not an m in the word slope, but that is the symbol that we use. There are 4 types of slope. Positive slope means it rises as you move from left to right. Negative slope falls as you move from left to right. Zero slope, or slope equal to 0, means it's flat or horizontal. And this happens when you have a y equals a number equation. So if this was like 2 tick marks, this would be y equals 2, and there's no x in that equation. And the last is undefined slope. And undefined happens when it's a vertical line, and the x is there without the y. So this would be like 1, 2, 3. Let's say x equals 3. Slopes of parallel lines is, well, and it's the theorem, but something we already know. In a coordinate plane, two distinct non-vertical lines are parallel if and only if they have the same slope. So parallel has the same slope, same rise, same run. In any two vertical lines are also parallel. You just can't compare those slopes because they're undefined. So any two vertical lines are also parallel. Slopes of perpendicular lines, also from algebra, we know that two non-vertical lines are perpendicular if and only if the product of their slopes is -1, or their slopes are opposite reciprocals of each other. Horizontal lines are always perpendicular to vertical lines. So one has the slope of 0, flip that, change its sign, and it's undefined, and that would be the vertical one. So if you have the slope of one line and it's, let's say, 2/3, the slope of a line perpendicular to it, well, parallel to it would be the same, 2/3. The slope of a line perpendicular to it would be -3/2. So you flip it and change the sign. If it started negative, you would change it so that it's positive. Example 1 says, complete with sometimes, always, or never. The slope of a vertical line is blank 0. We just said the slope of a vertical line is undefined, so it is never 0. B, the slope of a horizontal line is blank 0. Horizontal line is always 0. C, the slope of a line that rises to the right is blank positive. It's always positive if it rises as you move to the right. And the slope of a line that falls to the right is always negative. Example 2, find the slope of the line through the 2 points named. So for each of these, we're going to do y2 minus y1 over x2 minus x1. Looking at A first. So these could be our x1, y1s, and this could be our x2, y2s. So 5 minus 4 over -4 minus a -3, which becomes plus. And I get 1 over -1, and that's -1. Next one, -2 minus a -3 over -1 minus 6. Minus a negative becomes positive, and this is 1 over -7. Now that negative could be on the bottom, out front, in the top. It doesn't matter as long as it's somewhere on there. C, -4 minus a -4 over -3 minus 8. Minus a negative becomes plus, and I have 0 in the numerator. When 0 is in the numerator, my answer is 0. And 9 minus a -2 over -6 minus a -6. This becomes 11 over 0, and that's undefined. If you had plotted those last two, C would have been a horizontal line, and D would have been a vertical line. Example 3, complete the table for R being parallel to S and R being perpendicular to T. So R and S are always going to be the same. This would be -1/2. T is the opposite reciprocal. Flip it, change its sign. Now for B, we got to work backwards. So if it's 1/6, the opposite reciprocal would be -6, and parallel would be the same. C parallel to R, so these would be the same, and then flip it and change its sign. Same for D, these would be the same, flip it and change its sign. Oh, that's going to be positive, 1/4. E just gives you a variable, A by itself. Make it its reciprocal, change its sign would be -1 over A, and then both of the first ones would be the same. And the last one, I would do -4 over 3B, and it would be the same for R. Example 4 says if R is parallel to if R is parallel to S and R is a horizontal line, what's the slope of S? Horizontal lines have slope that are 0. 5, K is perpendicular to N n has a slope of 0. What's the slope of k? Well, the reciprocal of 0, even if you change its sign, is undefined. Now we get to the slope-intercept form of a line, also something from Algebra 1. So the slope-intercept form of a line is y equals mx plus b, where m is the slope and b is the y-intercept. For these examples, we're going to find the slope and the y-intercept, and then we're going to graph. So if you look at A, I get 2x minus 3y equals 6. So if I want to put it into slope-intercept form, I have to solve for y. So I would get negative 3y equals, I'm going to subtract the 2x from both sides, and then divide everything by negative 3. And the equation is y, because these cancel, equals negative 2 over negative 3, but positive 2/3 x. 6 divided by negative 3 is negative 2. Okay, I just pasted this graph from the next slide. So I use the b, which is the thing that's by itself, and that's my y-intercept. I start on the y-axis at that point, so negative 2. Then I use my slope as my rise over run. So I'd go up 2 and to the right 3 and plot a point. You could also reverse both of those things and go down 2 and to the left 3, and you'd still have your same line. So this is A. B is already in slope-intercept form. So, sorry, I didn't label this before. That would be your slope. So the negative 1/4 is your slope. And the B is 2. So your y-intercept is actually 0, 2. I'd go to the y-axis, plot 2, and then negative 1/4 is down 1, and 1, 2, 3, 4 to the right 4. If you reverse it, it's up 1 and to the left 4. And the last one, C, is one of your special cases. There's a y, there's no x, which means the y is always negative 3. If the y is always negative 3, this would be a horizontal line. The y-intercept is 0, negative 3. And the slope is 0 because it's horizontal. Okay, so now we're going to kind of put the last two things together. This one says, write the equation of the line that passes through point negative 1, 1 and is parallel to the line with the equation y equals 2x minus 3. Now, when you're doing these questions, you actually have two choices of what you can plug into. You can plug into the y equals mx plus b like we just looked at, which is slope intercept. But you can also use what's called point slope. And that's y minus y1 equals mx minus x1. In both cases, you still need a point and slope. So we have the point. This would be our x1, our y1, or our xy. And we have to find out what's the slope of a line parallel to this line. So what we need from this line is its slope, which is 2. And the slope of a line that's parallel to it would also be 2. So I'm going to do it with slope-intercept form, and then I'll do it with point slope. So the first thing I would do is take my y equals mx plus b and plug in the y for the y. So 1 equals the m, which is 2, the x, which is negative 1, plus b. And I get 1 equals negative 2 plus b, add the 2, and b is 3. Then I take and plug back in the m and the b. So y equals 2x plus 3. That's one way to find it, using slope-intercept. The other way is using point slope. So I use this equation. Y stays as y, minus I use the 1 as my y1. M is 2. The x stays as x. The x1 is negative 1. So minus a negative 1. I get y minus 1 equals 2 times, this is plus, x plus 1. Distribute the 2. Y minus 1 equals 2x plus 2. And then add the 1. So both ways get you the same answer. Both ways are acceptable. It's just a matter of preference. All right, example 7. Write an equation of the line J passing through the point 2, 3 that is perpendicular to line K with the equation 2x plus y equals 2. So I have the point again. This time, this is not in slope-intercept form, so I can either move the 2 to the other side, the 2x, so it'd be negative 2x plus 2. Then grab the slope. Or a shortcut, so this is in standard form. When they're both on the same side, the shortcut for the slope is negative a over b. The a is what's in front of the x, so negative 2 over the b is what's in front of the y, would be 1. So you can also use that shortcut to get the slope. Either way, that's the slope of a line that's perpendicular to what we want. So to find the slope of our perpendicular line, we're going to flip it and change its sign. So I'm going to use 1/2 and the point 2, 3. Again, I'll use both methods so that you can choose. The slope-intercept, y equals mx plus b. Y is 3, m is 1/2, x is 2, plus b. 3 would equal 1/2 of 2 is 1. Subtract the 1. B is 2. And then I plug back in the m and the b. So it'd be 1/2 x plus 2. Or slope-intercept or point-slope form, y minus, this is my y1, equals m x minus, this is my x2, or my x1. Y minus 3 would equal 1/2 x minus 1, because I'm going to distribute it to both. Add the 3. And y equals 1/2 x plus 2. Same answer. Both methods good to use. All right. Last question says, find the distance from point 1, 0 to the line y equals negative x plus 3. So if you want to give yourself a visual on this, like if I actually graph this, the point 1, 0 is here. And if I want to graph this line, I'd go to positive 3. My slope is down 1 and to the right 1. So remember that the distance from a point to the line, we use the shortest segment and we use what's perpendicular to that line. So I need to find the distance from this point to this point. Point 0 or 1, 0 to point 2, 1. So I get my x1, y1, x2, y2, 1, or the square root of 2 minus 1 squared plus 1 minus 0 squared. Distance formula, 1 squared, square root of 1 plus 1, which is the square root of 2. If it had, you approximate it, that's just a little bit bigger than 1. If you're actually finding it on a calculator, you might do that. If you're keeping exact, it would be square root 2. Now, if it wasn't as easy to spot, then what I would have to do is figure out what would be perpendicular to this. So because this slope is negative 1, the slope of the line perpendicular to it would be 1. Flip it, change its sign. So I'd go from here up 1 and to the right 1, and that's where I'd also get that coordinate point from. All right, that wraps up the video for 3-4 and 3-5. Have a great day.